it's just wonderful to be here. I mean, this is just such a fantastic opportunity. And you can see how I shared my screen with our plenary speakers. I mean, we're just so fortunate. We got the tops in terms of our 4 speakers, Emmanuel, Martin, Carrie, and Vindelin. I hope you get to attend their talks. It's just a great pleasure to host people whose research is of this caliber. Also, what about our shining stars, the stars that are rising? So these are our early career speakers. They're our rising stars. And we're really fortunate. Right after I finish, Nina will give us her plenary. It's an honor to be part of this. The last thing I wanted to show everyone, and Life mentioned this, this is the more interactions. You get to it from the program and you go down to more interactions and you see Ask Me Anything. So JC and we were able to get a number of very well-known probabilists and statisticians to donate 30 minutes of their time to have a Ask Me Anything session. I've done this before. It's a blast. Check it out. I think you're going to really enjoy it. All of this, I mean, Life says this was a low budget type project, but Life worked very hard along with all of his team. The members of the Bernoulli Society and IMS all supported this. So how do we ensure that things like this can happen in the future? It would be great if people could join the Bernoulli and IMS societies so that we can ensure that this kind of innovativeness can continue into the future. It's an honor to be part of all of this. Okay, we have 3 minutes. This is the 3 minutes before Nina's talk. This means you have time to get your coffee or tea, unless you're on the other side of the world from me, in which case it's time for your glass of wine. Thanks so much.
Susan, could you please stop the screen sharing so that Nina can share her screen?
I will do that.
This looks very good, Nina. No gray boxes this time.
Okay, that's good.
Okay, well, thank you very much for joining. My name is Ivan Corwin. It's a pleasure to be introducing Nina Holden. As you should see, hopefully on the screen, Nina is one of 3 recipients of the 2019 2020 Bernoulli Society New Researcher Award. She's currently holding a junior fellowship at the Institute for Theoretical Studies in ETH Zurich. In 2021, she'll arrive at Courant Institute as an associate professor. So Nina has a very impressive list of publications. I know I've looked over the years and seen it grow quite dramatically. Her focus primarily is on Liouville quantum gravity, and I think we'll learn about that and connections to random planar maps and SLD in today's talk. However, she also is very balanced. She spent time at Microsoft Research and has pursued a number of questions related to trace reconstruction, allocations and matching, and graph limits. So Nina received her PhD from MIT under Scott Sheffield in mathematics just 2 years ago in 2018. And before that is from Norway. So today, she'll be regaling us with the story of Liouville random surfaces and their central charge. So let me stop sharing, and Nina can resume sharing. I'll just say there can be a very active discussion in the chat, and I hope that people will really take advantage of that. And I look forward to seeing what people have to say. All right, thank you. All right, so Nina, you can take over now.
So first, thanks to Ivan for the introduction, and thanks to the Bernoulli Society for the prize. I also want to thank the organizers of this symposium. I think it's very nice that we're able to gather virtually now, as meeting in person is difficult. And it looks like it'll be a very exciting week with lots of experimental ways of interaction. So I will be talking about Liouville random surfaces and their central charge. This is based on a joint work with Ewan Gwynn, Josh Pfeffer, and Guillaume Remy. And Ewan Gwynn will be sitting in the chat, and he will answer any questions you may have during the talk. So we start by asking the question, how can you sample a surface uniformly at random? To answer this question, we first need to specify what we mean by a surface, and then we need to put some natural probability measure on this set of surfaces. One natural approach to the problem is to discretize it. A planar map is a natural model for a discrete surface, and we get a random surface by putting the uniform probability measure on some collection of planar maps. To be more precise, a planar map is a graph drawn on a sphere, which is viewed modulo continuous deformations. For example, the left and the middle planar map in the figure are considered to be the same because one can be obtained from the other by doing a continuous deformation. The middle and the right planar map, on the other hand, are not considered to be the same. For some natural number n, there are finitely many maps which have exactly n edges, and we get our uniform surface by choosing a planar map uniform at random from this finite collection of planar maps. So one natural question is what happens when we send the parameter n to infinity. We can ask whether the planar map m sub n is converging in some sense in the scaling limit. To answer this question, we first need to specify for which topology we want to prove convergence. One possibility is to prove convergence of the planar map as a metric measure space. A planar map is a metric space if we equip it with the graph distance, and it is a metric measure space if we also give each vertex a certain mass. It turns out that if we want the diameter of the planar map to be of order 1, then we should let adjacent vertices have distance n to the power minus a quarter. And we also give each vertex mass 1 over n, so that the total mass of the planar map will be of order of 1. It has been proved by Logal, Mirmont, and others that many types of uniform planar maps, they converge in the scaling limit, and the limiting object is an abstract metric measure space, which is known as the Brownian map. It's also possible to prove convergence of planar maps under conformal embedding. So you remember that planar maps are only defined modulo continuous deformations, so there is not a unique way to draw it. In the left figure, the planar map has been drawn in such a way that each edge has a length which is as close as possible to the other edges. Whereas in the right figure, the planar map has been embedded into the Euclidean sphere S2. It is possible to define such embeddings, which can be viewed as discrete approximations to a conformal map. When we embed the planar map, then we get a random metric, and we get a random measure on the sphere. This random measure is defined such that the mass of some open subset of the sphere is defined to be the mass of the vertices which are contained in this set. The distance between 2 points on the sphere is defined to be proportional to the graph distance between the embedded vertices which are closest to these 2 points. And it is believed that for a large class of conformal embeddings, then this measure and this metric converge in the scaling limit, such that the limiting object is independent of the particular choice of embedding that we chose. Such a scaling limit result has been proved in one particular case. It has been proved for the case when the embedding is chosen to be an embedding known as the Cardi embedding, and when the planar map is a triangulation, which means that all faces have exactly 3 edges. The limiting object in this convergence result is a Liouville quantum gravity surface, and that's the object I want to introduce next. In order to introduce a Liouville quantum gravity, we first need to introduce the Gaussian free field, and we start by considering the discrete Gaussian free field. We consider a rescaled version of Z2 restricted to the unit square. If we have a function defined on the vertices of this lattice, then we can define its Hamiltonian by considering the sum of the squared differences between adjacent function values. The discrete Gaussian free field, it is a random function which is defined such that the probability density relative to the product of Lebesgue measure is proportional to e to the power minus the Hamiltonian. In order to get a finite measure or a probability measure, we also need to introduce some additional constraints. For example, we can introduce some boundary data. It's not difficult to prove from this definition that at any fixed point, the value of the Gaussian free field will be a normal random variable, and it will be a normal random variable which has a variance of order log n. The expected value, so if we fix the boundary data of the Gaussian free field to be 0, then the expected value of this normal random variable will also be equal to 0. There is also some covariance between the function values at different points, so that the covariance between the values at points z and w is of order the logarithm of the inverse distance between the 2 points. One way to define the continuum Gaussian free field is to say that it is the limit of the discrete Gaussian free field when n goes to infinity. We see that the discrete Gaussian free field is diverging logarithmically when n is going to infinity, so it's not obvious how to make sense of this object. And in particular, the Gaussian free field is too rough and irregular to be well defined as a function. But it turns out that the continuum Gaussian free field is well defined as a random distribution or a random generalized function. This means that it's not possible to evaluate the Gaussian free field at a particular point, but we can, for example, take the average of the Gaussian free field over some open set. We can integrate it against some smooth test function, and so on. A Liouville quantum gravity surface is a surface which can be written on the form e to the power gamma h times the standard Euclidean metric. Here gamma is a parameter between 0 and 2, while h is an instance of the Gaussian free field. This definition of a Liouville quantum gravity surface does not make literal sense because h is a distribution and not a function, so it's not obvious what e to the power gamma h means. But several observables of this surface can be shown to be well defined, and in particular one can define rigorously the measure and the metric or distance function associated with the surface. The idea of these constructions is to let the h sub epsilon be some regularized version of h, then use h sub epsilon to define a measure and a metric, and then show that the resulting measure and metric converge when we send the regularization parameter epsilon to 0. Measures of this kind, so the construction of such measures goes back to the 70s and the 80s, while the construction of this metric or distance function was only completed last year. So the construction of such a measure and metric, it can be done for any gamma between 0 and 2, but it turns out that it is the special value gamma equal to square root of 8/3, which describes the scaling limit of uniformly sampled planar maps. I can also mention that there will be many talks during this conference about Liouville quantum gravity, including, for example, plenary talks of Shin-sun and Vendrin Werner on, depending on the time zone, Wednesday, Thursday, and Friday. So we have seen that uniformly sampled planar maps, they converge in the scaling limit in two different ways. Viewed as an abstract metric space, they converge to the Brownian map, and viewed and under conformal embedding, they converge to Liouville quantum gravity. Mueller and Sheffield proved in a series of works that the Brownian map is actually equivalent to Liouville quantum gravity. More precisely, they proved that an instance of the Brownian map has a canonical embedding into the complex plane, where such that the induced area measure and metric are given by the measure and the metric associated with a Liouville quantum gravity surface. So in particular, the metric measure space defined by a Liouville quantum gravity surface is equal in law to the Brownian map. So far in the talk, we have been considering uniform random surfaces. In string theory and conformal field theory in the 80s, people were also interested in particular non-uniform random surfaces. In particular, people including, for example, Polyakov was interested in surfaces whose law has been reweighted in a certain sense by the determinant of the Laplacian of a surface. So what does this mean? So in the discrete setting, it's not difficult to make this rigorous. So if we let C be what we call a matter central charge, which is some real number, then we sample, we let M be a random planar map, which has been sampled such that the probability of sampling a particular planar map is proportional to the determinant of the Laplacian of this planar map to the power minus C over 2. The Laplacian of a planar map is a particular linear operator which has been derived from the adjacency matrix of the map. So one reason that such planar maps are interesting is a physics heuristic, which is saying that when C is a positive integer, then the law of the planar map M has been reweighted in some sense by the number of ways to embed the planar map into some C-dimensional space. I can also mention the matrix tree theorem, which is saying that the determinant of the Laplacian is also equal to the number of distinct spanning trees that the planar map admits. So by a physics heuristic known as the DDK ansatz, then these non-uniform planar maps are also believed to be related to Liouville quantum gravity. So the DDK ansatz is saying that the planar map M is converging in a scaling limit to a Liouville quantum gravity surface with parameter gamma, where gamma and C are related to each other by the shown formula. The DDK ansatz was stated for C less than or equal to 1, which corresponds to the parameter gamma varying between 0 and 2. Going back to the previous slide, we see that these scaling limit results, they are a verification of the DDK ansatz in a special case when C is equal to 0, which corresponds to gamma being equal to the square root of 8/3. So when the mathematical understanding of the DDK ansatz is not as good when C is not equal to 0, but there has been made some progress also for other values of C less than or equal to 1. So it is believed and in certain cases proved that the determinant of the Laplacian of some planar map to the power minus C over 2, it is equal to or can be approximated by the partition function of certain statistical physics models. So the figure is showing some examples. So for example, if we want to sample a planar map in the C equal to 1/2 universality class, then we see that C equal to 1/2 corresponds to the Ising model. So one way of doing this is to sample a planar map such that the probability of picking a particular planar map is proportional to the Ising model partition function on this planar map. Convergence to Liouville quantum gravity has been established for several types of planar maps reweighted by the partition function of a statistical physics model in the so-called mating of trees topology. The mating of trees topology is a topology which does not directly capture metric and conformal properties of the planar map, but the idea is instead to show convergence of a particular observable of the planar map to the associated observable in the continuum. There's also been various progress on proving that random planar map exponents are equal to the corresponding exponents in the continuum. For example, there are various results on what is known as stable maps. There are some results for the O of n loop model, for the volume growth exponent of various planar maps, and also various exponents for the Ising model. There has also been some recent progress by Ang, Park, Pfeffer, and Sheffield, which we'll come back to later, which is saying that different Liouville quantum gravity surfaces, in some sense, are related by reweighting by the Laplacian determinant. So in other words, that makes sense of reweighting by the Laplacian determinant directly in the continuum. And they show that different Liouville quantum gravity surfaces are related, as one would expect, by doing error weighting by this Laplacian determinant. So here you can see simulations of planar maps for 3 different values of C. In the right figure, we have C equal to 0, so we have a uniformly sampled planar map. And in the other figures, we have planar maps corresponding to C equal to -5 and -7. So looking at the figure, you can maybe see that when C goes to -infinity, then the planar map will be looking, the geometry of the planar map will be closer and closer to the geometry of the standard Euclidean sphere. When C is large, on the other hand, then the planar map will typically have long tentacles. And it is conjectured in the physics literature that when C is greater than 1, then the random planar map will converge in the scaling limit as a metric measure space to the continuum random tree. So to sum up what we have seen so far, we have seen that random planar maps reweighted by the Laplacian determinant to some power, they converge to Liouville quantum gravity when C is less than 1. And this was first conjectured according to the DDK ansatz, and different versions of this convergence result has been established rigorously also mathematically. When C is greater than 1, on the other hand, then it is believed that we get a continuum random tree in the scaling limit. So if we look at the formula which relates C and gamma, and we plug in a value for C, which is bigger than 1, then gamma will be a complex number. So one natural question is whether we can define some non-trivial geometry for Liouville quantum gravity, also when C is greater than 1. So one of the main goals of this talk is to address this question, and we will see that the answer is yes when C is between 1 and 25. And the work I'm presenting in this talk, it is the first probabilistic work which is studying a model for Liouville quantum gravity, which gives a non-trivial geometry when C is greater than 1. So far we have seen that planar maps, they provide a natural, they are discrete versions of a Liouville quantum gravity surface. And now we will be looking at another discretization of a Liouville quantum gravity surface. We start by considering a Gaussian free field H in the unit square and the associated Liouville quantum gravity area measure. Then we divide the square into 4 smaller squares, and we divide each square into further into 4 smaller squares, and we do the same thing again. So before we started this square subdivision, we had fixed some small parameter epsilon, and every time we reach a square which has Liouville quantum gravity area, which is smaller than epsilon, then we stop, then we don't divide this square. So in particular, the 3 bigger squares you can see in the figure, they all have Liouville quantum gravity area, which is smaller than epsilon. We divide the squares again, and you can see that now we have reached even more squares which have a Liouville quantum gravity area less than epsilon. And we keep subdividing until all the squares have area less than epsilon. This is the exact same picture, except that I've given the different squares a different color depending on their side length. And this is again the same picture as before, except that it is for a simulation of a Liouville quantum gravity surface. Here you can see simulations for 3 different values of gamma. So in the right figure, you can see that when C and gamma both are large, then there will be some regions with very big squares and some regions with very small squares. Well, we can see in the left figure that when gamma and C are smaller, then the squares are not as variable in size. And this happens because when gamma is large, then the Gaussian free field is giving us a bigger distortion of the Lebesgue area measure. As you may recall from earlier, that the Liouville quantum gravity surface is associated with a measure mu and a distance function, or metric d. We let d sub c be the Hausdorff dimension associated with a metric big D. It can be proved that the volume of some metric ball is of order radius to the power d sub c. So this is natural because in d-dimensional space, then volumes typically scale like radius or diameter to the power d. The metric ball we consider here is the metric ball for the metric d. The precise value of d sub c is not known, but in the left figure you can see the best known rigorous upper and lower bounds. Whereas in the right figure, you can see simulations of metric balls in the Liouville quantum gravity surface. The color of a point is indicating its distance to the origin, while the points which have distance more than 1 to the origin, they are colored in black. So going back to the square subdivision, then we can observe that the square subdivision is defining a planar map. So we get a planar map by identifying each square with a vertex, and we say that two vertices are connected by an edge if and only if the corresponding squares share an edge. We pick some arbitrary vertex and we color it black. And then we look at the metric balls in our planar map. So these are metric balls for the graph distance, and we let them be centered at the black vertex. In the figure, you can see the case of radius 1. Here you can see the case of radius 2. Here the case of radius 3, and so on. So it turns out that this planar map of squares, that important properties of the Liouville quantum gravity surface are reflected in this planar map of squares. So for example, it's possible to show that also in the planar map of squares, the volume of metric balls is growing like the radius to the power d sub c. Here d sub c is again the Hausdorff dimension of the continuum surface. We consider a ball for the graph metric, and the volume of a ball is the number of squares that it contains. It's also possible to show that closely related discretization of a Liouville quantum gravity surface is converging back to the original Liouville quantum gravity surface under a discrete conformal embedding, which is known as the Tutt embedding. So both of these results, they indicate that the square subdivision planar map is a natural model for Liouville quantum gravity, because important properties of the Liouville quantum gravity surface are reflected in the planar map of squares. We can even conjecture that the graph metric of the planar map of squares is converging the scaling limit to the Liouville quantum gravity metric. We can consider 2 points, z1 and z2. We consider the graph distance between these 2 points, and we can conjecture that when we appropriately rescale this graph distance and we send the size of the squares to 0, then this graph distance is converging to the Liouville quantum gravity distance between the points as measured by the LQG metric. Ding and Dunlap, they considered a related discretization of the surface, and they proved tightness for the metric for this discretization. So next we will see that Liouville quantum gravity area measures, they can be approximated in terms of Gaussian free field averages. We will see that the Liouville quantum gravity area of the square S in the figure, it can be approximated in terms of the average of the Gaussian free field along the red circle. So to be more precise, it turns out that the Liouville quantum gravity area of the square to the power 1 over s, it is approximately equal to the side length of the square to the power q times e to the power the circle average. Here the parameter q is the parameter which is known as the background charge, and it's given by 2 over gamma plus gamma over 2. In the table you can see the relationship between the various parameters of interest. When c, the third column corresponds to the classical case when c is less than or equal to 1, while the fourth column corresponds to the case when c is between 1 and 25. So what you can pay special attention to is that in the classical case, when c is less than or equal to 1, then gamma is real and between 0 and 2. When c is between 1 and 25, on the other hand, then gamma will be a complex number with modulus equal to 2. On the other hand, this parameter q, the background charge q, is actually real in both cases. By the approximation result on the previous slide, then we can do an approximation to the square subdivision model by considering Gaussian free field averages. We define a new square subdivision model where we divide the square s if and only if the side length of the square to the power q times e to the power of the Gaussian free field circle average is greater than epsilon. By the approximation result on the previous slide, this variant of the square subdivision model should be approximately equivalent to the original variant, which is defined in terms of Liouville quantum gravity areas. And there is one interesting observation we can make, which is that this new variant of the square subdivision model, it also makes sense when the central charge C is between 1 and 25. So why is this? So we can see why this is the case by looking at this table of the parameters. So what we can recall is that in the original square subdivision model, then we needed to have a Liouville quantum gravity area measure, and therefore we needed the parameter gamma to be between 0 and 2. For this new variant of the square subdivision model, on the other hand, then we only need the parameter q to be real, while gamma can be complex. The reason for this is that it's only the parameter q which is entering into the model. So since the parameter q is real when c is between 1 and 25, then we see that the square subdivision model we are studying now, it also makes sense for c between 1 and 25. So we let M be the planar map of squares, which is defined by doing square subdivision with Gaussian free field circle averages. And this planar map M is our model for Liouville quantum gravity when C is between 1 and 25. So one of the first things that one can prove is that this square subdivision model, it has a phase transition at C equals to 1. When C is less than 1, then the square subdivision is terminating with probability 1. So one way to see this is that when C is less, is that the Liouville quantum gravity area measure is non-atomic. But then on the other hand, when C is between 1 and 25, then it holds with probability converging to 1 when epsilon is sent to 0, that there will be certain points where we keep subdividing squares forever. So a point where we keep subdividing squares forever, we view this as a point of infinite mass. It is natural to view it as a point of infinite mass because the square subdivision model was defined such that each square has approximately the same Liouville quantum gravity size. It's possible to show that there is a dense set of points which has dimension 2 minus q squared over 2. Such that for each point in the set, then when epsilon is sufficiently small, we keep subdividing the squares containing this point forever. For some fixed value of epsilon, then we will typically see a picture as we see in the slide. So in the slide, you can see that we have 3 regions where there are points where we have kept subdividing forever. When we decrease the value of epsilon, then it will typically be more and more points where we keep subdividing forever. So you may recall from earlier that when we consider random planar maps reweighted by the Laplacian determinant, then it is believed that we get the continuum random tree in the scaling limit when the central charge C is greater than 1. Therefore, we can view the continuum random tree as a finite volume model for Liouville quantum gravity with C greater than 1. We view it as a finite volume model because both the diameter and the total mass of the continuum random tree is finite. Our model for Liouville quantum gravity with C between 1 and 25 has a very different nature. We view it as an infinite volume model for Liouville quantum gravity for C between 1 and 25 because we have these infinite mass points where we keep subdividing forever. And these points can be shown to lie at infinite graph distance from the rest of the surface. So we can still ask whether our model is the correct probabilistic model for Liouville quantum gravity when C is between 1 and 25. A recent work of Ang Park, Pfeffer, and Sheffield gives some justification for our model because it says that, that the square subdivision planar map for different values of C in some sense are related by doing a reweighting by the Laplacian determinant. To be precise, they consider some central charge C, they let epsilon be positive and they let n be a natural number. Then I let M be a planar map, which is obtained by doing square subdivision with central charge 0, square size epsilon, and conditions such that a number of vertices is equal to n. Then they reweight the probability measure by the Laplacian determinant to the power minus C over 2. I will not define the exact Laplacian determinant which is used when doing this reweighting, but I can mention that it is defined by doing a particular by considering a particular smooth approximation to the field H, and then applying a formula which is known as the Polyakov-Alvarez formula. And then they show that under this reweighted probability measure, then the law of the planar map M is the law of a planar map, which has been obtained by doing square subdivision for central charge C. So this gives some justification for our model because it shows that the square subdivision planar map for different values of C are related to each other by doing a reweighting by the Laplacian determinant. So what results are we able to prove about the model? So first we prove a result which is suggesting that the dimension of a Liouville quantum gravity surface for C between 1 and 25 is infinite. So what we prove is that if we consider the volume of a metric ball of radius r in our square subdivision planar map, then this is growing faster than any power of the radius. So here we consider a metric ball for the graph distance, and as before, the volume of the metric ball is defined to be the number of squares it contains. Heuristically speaking, we see such superpolynomial growth because the planar map of squares has some properties in common with a supercritical Galton-Watson tree. To be a bit more precise, so nearby these points where we keep subdividing squares forever, then the planar map has some properties in common with a supercritical Galton-Watson tree. And we know that the supercritical Galton-Watson tree has superpolynomial or even exponential growth, and we can show superpolynomial growth also in our setting. We also show that point-to-point distances are polynomial in epsilon. So we consider 2 points Z1 and Z2, and we look at the graph distance between these 2 points in the planar map of squares. And then it can be shown that this graph distance is polynomial in a square size epsilon. A recent work of Ding and Nguyen, they actually get tightness for such distances. However, they are considering another model for Liouville quantum gravity with a C between 1 and 25. They consider a model which is known as Liouville first passage percolation. This is defined such that the distance between 2 points Z1 and Z2, it is obtained by considering a path connecting the 2 points, then integrating the exponential of the Gaussian free field along this path, and then take the infimum over all paths. Yeah, and I can also mention that when C is smaller than 1, then it can be proved that this Liouville first passage percolation distance is converging in probability to the Liouville quantum gravity metric. And this is actually how this Liouville quantum gravity metric is constructed. It is constructed by first proving tightness for the distances as defined via Liouville first passage percolation, and then by showing uniqueness of subsequential limit by satisfying that, by proving that any subsequential limit is satisfying a particular list of axioms. So we also prove that that our square subdivision planar map is satisfying a variant of the KPC formula. The KPC formula is a formula which is relating the Euclidean and Liouville quantum gravity dimension of random fractals. To explain what the KPC formula says, we assume that X is some fractal in the unit square, independent of some background Gaussian free field. Then in the left figure, I have divided the unit square into smaller squares of side length epsilon. And then if the number of squares which intersect x is of order epsilon to the power minus d sub x, then we say that d sub x is the Euclidean dimension of x. We do the same thing in the right figure using the square subdivision model. If the number of the squares intersecting the fractal in the right figure is of order epsilon to the power minus d sub x superscript c, then we say that d sub x superscript c is the Liouville quantum gravity dimension of the fractal. The KBC formula is an explicit quadratic formula which is relating these two dimensions. It was first derived heuristically in the physics literature in the 80s, and in more recent years, very different versions of the formula have been rigorously proved in the math literature. So the KBC formula, it was typically used by the physicists in order to predict the Euclidean dimension of random fractals. So in many cases, it's possible to heuristically calculate the Liouville quantum gravity dimension by using combinatorics on a planar map. And then by plugging into the KBC formula, one gets the Euclidean dimension of the random fractal. One famous example of this is the case of the Brown intersection exponents. So they were derived by Bertrand du Plantier using the KBC formula. And then they were, their values was found rigorously several years later by Lawler, Schramm, and Werner by using SLE techniques. So we show that our square subdivision model is satisfying some variant of the KBC formula. We consider some fractal which has Euclidean dimension d sub x, and we show that the number of squares in square subdivision planar map which intersects this fractal is what one would expect according to the KBC formula. When the dimension d sub x of the fractal is greater than q squared over 2, then the KBC formula gives a complex answer for the Liouville quantum gravity dimension. And in this case, we show that the number of squares that intersect the fractal is infinite. It is possible to show that the number of squares that intersect the fractal is infinite if and only if x is intersecting some of these infinite mass points, meaning the points where we keep subdividing squares forever. So finally, I want to state a few open problems related to this talk. So first, we can ask about scaling limit results for planar maps, whose law has been reweighted by the determinant of the Laplacian to some power minus c over 2. And as we saw earlier, this is just partly understood also in the classical case when c is less than or equal to 1. We can also ask for scaling limit results for various coarse-grained models for Liouville quantum gravity. So these are simplified models for Liouville quantum gravity, which are defined directly in the continuum via a Gaussian free field. For example, it's possible to consider the square subdivision model and try to prove that it converges as a metric measure space in the scaling limit. We can also ask for natural combinatorial random planar map models when c is between 1 and 25. We saw earlier that when c is smaller than 1, then Liouville quantum gravity surfaces, they arise as the scaling limit of planar maps, which has been reweighted in various ways. But if we consider such a reweighted planar map for c greater than 1, then it is believed to converge to the continuum random tree. And we can ask whether there are some natural combinatorial random planar map models which are in the same universality class as our planar map of squares when c is between 1 and 25. We can also ask questions directly in the continuum. So you may remember that when c is between 1 and 25, then the parameter gamma is complex and it has modulus equal to 2. And we can ask whether we can make sense of e to the power gamma h times the Lebesgue measure for such values of gamma. And if the answer to this question is yes, we can ask whether the resulting object has any relationship to our square subdivision planar map. For certain values of gamma, one has actually managed to make sense of e to the power gamma h. And in this case, e to the power gamma h is defining a random distribution instead of a random area measure. But the case when the modulus of gamma is equal to 2 is falling outside the range for which this construction works. One can also try to make sense of the path integral approach to Liouville quantum gravity when C is greater than 1. So the field H, which we studied in this talk, is actually not, so that was a Gaussian free field, but the field which is describing the scaling limit of random planar maps is actually not an exact Gaussian free field, but it's instead, it is a field whose law has been, it is a field which is a Gaussian free field whose law has been reweighted in a certain way by the Liouville quantum gravity area, which the field is inducing. So one way to make to construct such a field is to do the path integral approach. So the idea of the path integral approach is to consider Lebesgue measure on the space of functions, and then reweight this by e to the power minus the Liouville action S sub L. So this definition of some random function phi doesn't make rigorous sense. For example, it doesn't make rigorous sense because the Lebesgue measure on the space of functions is not well defined. But for C smaller than 1, then this path integral approach has been made sense of rigorously. For example, in work of David Kupiainen, Rhodes, and Vargas. And we can ask whether some variant of this construction also works when C is greater than 1. One obstacle is this term e to the power gamma h, gamma phi in the action, which is complex when C is greater than 1. We can also ask about Schramm-Loewner evolutions for C greater than 1. So SLE is a one-parameter family of random fractal curves, which describe the scaling limits of statistical physics models. And SLE is associated with a parameter kappa, and for each value of kappa, there is an associated value of C, which is less than or equal to 1. So when C is less than 1, then there are a number of natural couplings between SLE and Liouville quantum gravity with this central charge. And we can ask whether it's possible to make sense of SLE for C bigger than 1, and whether there is any relationship between SLE and LQG also for C greater than 1. So there are various discrete models which are believed to converge to SLE, which also makes sense when C is greater than 1. But these models seem to not have scaling limits in the same sense as before when C is greater than 1. Finally, we can ask about the physical meaning of various complex numbers. So there are various formulas in Liouville quantum gravity which give complex answers if they are analytically continued to the regime where C is greater than 1. And we can ask whether these complex numbers, which are obtained via analytic continuation, have any physical meaning. Yeah, so that was the end of the talk. So yeah, now you can answer any questions if you have some. Yeah.
Yeah, well, thank you very much, Nina.
Yeah, thanks.
I love the graphics. They should make floors that have these sort of patterns. They're much more interesting. So I don't know that people can unmute themselves. So I think if people have questions, now would be a good time to put them into the chat, and then Nina can respond to them. So we can take a moment if people want to do this.
If people want to ask questions, they can raise their hands and we can unmute. Just okay. You can also do that.
Okay. So maybe I'll ask a question, and this is an obnoxious question, so feel free to ignore it.
Okay.
But what is the trajectory of this field? You know, what are the, for people who don't know so much about it, where is it going? Kind of what are the remaining big questions?
Okay. Well, so I guess depends a little. I guess there are many directions, and it also depends on, I guess, exactly how you define the field. But I guess some of the remaining open problems is to have a better understanding of this relationship between Liouville quantum gravity and random planar maps. So yeah, I presented some results in the talk, but especially for the case when the central charge is not equal to 0, then there are still a lot of open questions. For example, convergence of planar maps as metric spaces, and so on. Yeah, and under-conformal embedding. So that's one direction. I mean, there are lots of other directions one can also go in. One can look at try to make sense of some of this in higher dimensions. So far, everything is two-dimensional. One can also try to look more at something at the intersection of so there are somehow in the field there are two different approaches to constructing the objects we're looking at. There is the Liouville conformal field theory approach, and also another approach which is coming more from the planar map side, and one can try to prove more relationships between those two approaches. That's another direction. Yeah, that was a long reply.
I very much appreciate it. Are there other questions for Nina, either in the chat or people who want to raise their hands? Okay. Well, I think we should take this opportunity to thank Nina again for a really wonderful talk with all sorts of interesting content. So thank you very much, Nina.
Thank you.
And congratulations.